All right, for our final piece here of supervised learning, I'm going to consider one of the other top methods used for machine learning, which are not neural nets. So what we just had consider was classification trees and how it was a structured approach, principled approach for slicing through the data to look for the best way to separate that data. And what we're going to look at now is a pairing to that, which is what's called a supervised learning technique called support vector machine. And what support vector machine is one of the leading methods, pre-neural networks, for actually doing classification and clustering of data. And so again, it's a training paradigm where you give it labeled data. So I give you data plus labels, and so now you build a classifier. So if I give you new data, you're going to provide me labels from that data. So the way this works is very much like, it's sort of a generalization of linear discriminant analysis. So one of the reasons to consider linear discriminant analysis, even though it's not as commonly used in machine learning, is that it's sort of, in some sense, a foundational piece allowing us to start thinking about what support vector machine is actually going to do. And so let me sort of draw the pictures of what this is. In fact, this first picture will look very much like a linear discriminant analysis. I have some data with labels. So here are magenta and green balls. And so I already know what the labels are. And my goal then is to try to separate this data. So find a way to discriminate between those green balls and magenta balls. So one way to do that is to draw a line through here, or a hyperplane if this is higher dimensional. And so part of drawing that plane through there is a couple of things we want to think about. So first of all, there's going to be a vector W out to this plane. So this plane is right here, Wx plus b equals to 0. This defines the hyperplane. If you're on above this plane, Wx plus b is greater than 0, which means you're in the space of the green balls. If Wx plus b is less than 0, you're over here in the space of the magenta balls. So one way to think about what the classifier is going to do is, if I can find this plane, right, which is w dot x plus b equals to 0, then anything on either side will give me the classification I need. Now the goal in building this plane when I train the data is to build a plane which gives me the maximum margin between the data sets. In other words, how do I structure this plane so I can get the best separation, which is the largest margins? So here's one example of this where I have this vector here, orthogonal here to the plane, and once I have that, that gives me a good broad margin. However, here's a different plane that still separates the data well, but look at how thin the margins are now. So I would not want this plane, I'd want this plane. In many ways, when we did discriminant analysis, right, we were looking for what is the plane that gives me the best separation between class data, right? And so if I look at the right projection with discriminant analysis, I wanted the means of the data to be as far apart as possible with the smallest variances in the data when I look at it from the right angle. And so in some sense, this here is what we want, not this here, okay? So we want the largest margin between, and this is what we're going to do is we're going to set up an optimization algorithm to actually find this plane right here, okay? So we need to find the vector W, and we need to find the B. Okay, so that is the goal of the optimization. So how do we want to do this? Well, first of all, let's just think about this. So a linear support vector machine is just this plane here. This is the discrimination line. Okay, now notice we haven't done it. This is in some sense just simply the discriminant analysis we've done previously, but now we're going to set it up, instead of looking at the eigenvalue problem that we used before to solve this, we're going to actually sort of formulate an optimization problem and then generalize it a little bit from there. Here, what we're looking for in the data is higher dimensional data. We're looking for a hyperplane of separation. So that more broadly, this is some n-dimensional plane cutting through my n+1 dimensional data set. Okay, so you can go to very high dimensional data and try to draw a separation plane between magenta and green balls, for instance. And so what we're going to start looking at are quantities like this, an indicator function, y. So what y is, and this is going to be a quantity I can evaluate for every data point. So I can go to every single data point, and for every single data point, I actually ask the following question. If I put that data point into this, w dot x plus b, what I'm really looking to do is say, what is the sign of this? What I know is, if it was positive, I'm going to label that as a green ball. If it's negative, I'm going to label it as a magenta ball. So I'm really interested in the sign of this. So in fact, what I'm going to do with this is just simply, I don't really care what the value is. I just want to know if it's positive, +1, or minus, -1. There it is. So this is, that is the idea behind what we have here, is I just want to know what side of that plane I'm on. And this is a quantity that will actually map that for us, whether I'm positive or negative. Okay? So this is also going to be the basis of our optimization function, because what we want is to use this, which is my label, and compare it to the truth, because I've actually have the label for the truth, in order for me to evaluate how well does this hyperplane I've built. This is what we're going to construct. We're going to construct this hyperplane. We want to construct the hyperplane so we get as many of the labels correct as possible. Okay, that's the optimization that we're going to be doing. All right, so here's the optimization framework. We define this function here. This is going to be a loss function, L, which is basically looking at some value between y of j and y bar of j. So y of j is the actual label for the data. Is it a magenta ball? Is it a green ball? Which is either a +1 or a -1. And in here, y hat is going to be my label for that data given the hyperplane I have. So if I have a hyperplane here, all I got to do is take the data I have, the data point I have, project it onto my hyperplane, and ask what is the sign of this? This will either be +1 or -1. Now, the way this works is if I get it right, in other words, if the label was supposed to be 1 and I got a 1, then I get a 0 here. In other words, I got it correctly. However, if I get it wrong, in other words, it was supposed to be a 1, and I said it was a -1, then here I get a penalty term, a +1. So every time I get it wrong, I get +1. Or more succinctly, this is how you might think about this loss function here. I look at every single data point and I don't pick up a loss penalty if I get it right, so 0 contribution if I get it right. But if I get it wrong, I get dinged by +1. And of course you can play around with the penalization if you like, but here it's just a generic, every time you get something, one data point wrong, you get a +1. And of course your goal is to get them all right, so you would like not to collect any of these if possible, but of course you're gonna pick up some penalty. And so the objective will be find this hyperplane right here, this W and the B. What is that hyperplane that minimizes all the penalties I'm picking up, right? So I want to draw that plane so that when I get my labels and the actual labels, I make as few mistakes as possible. So this is kind of an obvious thing to do. However, the optimization itself is a little bit of a heavier lift. And it's a lot more complicated than, say, support vector machine, which just turns into a simple eigenvector problem on the statistics of the data. Okay, so here's the linear SVM optimization, linear support vector machine optimization. What you're trying to minimize is you're trying to find W and B so that you minimize this loss penalty. You want to constrain the length of W, so you don't want to make W so big that you create problems for yourself. You constrain the length of W, and then also here you try to basically look at the projection to be 1. So x of j projected onto W dot product is 1. Okay, so these is the subject to line, and you minimize this loss. So it's a constrained optimization. It's non-smooth. The reason it's non-smooth because your penalty term goes in discrete points. So it's, if you get 1 wrong, it's 1. You get 2 wrong, it's 2. It's not a smooth function. And so it's non-smooth, it's discrete, but it has a constrained optimization flavor to it. Now, the nice thing is, we're not going to talk so much about optimization algorithms so much in this, but one of the truly remarkable advances, there's 2 that have powered a lot of the machine learning in AI. One is just the incredible advancements in optimization architecture. So we have algorithms that can do these optimizations at scale. And second, computational resources to actually carry them out in practice, even for large data sets. So I won't go into sort of, in some sense, the details of how to do a constraint optimization with a non-smooth objective function. I'm just going to write down what the optimization is, with the idea here that you can look at this and say, okay, this is actually, the support vector machine has a principled mathematical architecture of an optimization, which is trying to find that hyperplane that best separates the data. And every time I don't separate it correctly, I pick up a loss term, which I'm trying to minimize just simply by adjusting the plane that I have available to me. Okay? So that is how we would think about the construction. Everything's going to come down to an optimization. By the way, all of neural nets are just an optimization as well. So this is what we're aiming towards in terms of building out machine learning. Underneath it all is just optimization. Machine learning is optimization. That's the basics. All right. So here is by the way, to make this, sometimes people don't want to do the optimization with this discrete, this loss that is not continuous but has discrete aspects. Instead, what people sometimes will do is instead just replace everything by just what's called a hinge loss. And the hinge loss makes everything smooth. So now you're doing optimization on a smooth loss function. And the hinge loss is just something like this. H of z is the max between 0 and 1 minus z. So as z goes from 0 to 1, this in fact varies smoothly from 0 and goes upwards from there, or 1 minus z. So okay, so this is just a way to make a hinge loss as the value of this h increases. Another one you have here. Remember, I'm going to decide whether this thing becomes whether I've actually got this thing. I get a 0 or 1, but now this thing here creates a smoother for me, so that now I'm doing essentially a smooth optimization routine for this. Okay, so that's the main idea behind support vector machine. Is in some sense it's a generalization of linear discriminants, but now we're just going straight after the optimization, whereas in linear discriminants we could actually cast everything in terms of an eigenvalue problem to solve. This is much more general, and as you'll see next, we can modify this up a little bit to make it really work in practice. Because nobody actually does linear SVMs in practice. What they do is instead something quite different, both for scalability and also for feature space. So normally what people actually do is, instead of working with the original variables, we actually lift the variables. So we take x and we project into functions of x. And this procedure here is incredibly important. So you're going to basically lift yourself from some finite n-dimensional space up into very high dimensional spaces towards infinity. And in fact, Cover's theorem from 1965 is one of the most important theorems of machine learning, which says if you want to do perfect discrimination with data, if you take large enough data, in other words, lift it into infinite dimensions, linear discriminants will work. That is sort of what Cover's theorem states, and is sort of a foundational piece for a lot of machine learning methodology. And this is, in some sense, an attempt to go to scale. So in other words, you say, I'm not going to work with x, I can work with functions of x. So I might project to x, x squared, x cubed, sine x, different functions of x to make an enriched higher dimensional space. And I'll show you an example of this in a minute that will hopefully make really clear what we're doing with this, with the entire goal that in this new space, a linear classifier can work. A hyperplane can more easily cut the data. Okay? So in other words, let me just say it more succinctly. I start with my data in the space that it's in, and I try to do a linear classifier, and I get a certain performance. By lifting it to higher dimensional spaces, I can improve the classification performance by lifting it to much higher dimensional spaces. That's the bottom line with support vector machines. And this is why they were so popular. You just lift up and you find yourself with quite improved performance, and largely because of these nonlinear SVMs. Now, of course, This also presents a computational challenge because every time you lift up there, you're doing a much larger optimization problems. But even that, people found ways around, which I'll highlight in a moment, okay? So let me give you an example of what this lifting is. All right, here's some data, an example. I have data in X1 and X2, okay? So this is my data set. And what I'm gonna do is project X1 and X2 into now 3 dimensions, X1, X2, and X3. And what X3 is gonna be is X1 squared plus X2 squared. So I can do this, right? So I'm lifting into 1 extra dimension. Now the reason I wanna do this is for a very nice example, which shows me then how I can do classification or linear hyperplane separation. And here's the example I want to show you, which is this right here. So what this is data. So the data originally lives in X1 and X2, which is on this plane. And if you look at this data, look at it. You have magenta balls on the outside, and in the middle you have green balls. So the ultimate discrimination line is this circle. But of course, I'm trying to separate the green data and the magenta data with a hyperplane. So there's only one way. If I look at the data in this original variable set, all I could do is cut this donut in half. And so I do a terrible job in discriminating between the magenta and green balls. However, that's the X1 and X2 plane. If I also lift it into the X1 squared plus X2 squared, I create this data set here. So I lift it now, and in fact, because I'm squaring it, the X1, X2 only get lifted up a little bit, whereas this outer ring, X1 squared plus X2 squared, gets lifted up a lot, which means I can actually slide a slice of a plane in between the green and the magenta balls very cleanly, right? So what I did is I used a hyperplane to separate this data here simply by lifting into a good variable set, okay? So that is the entire concept of SVM in a nutshell. Now, of course, this one is easy to look at. You can kind of see how is that I can take data in a ball and cut it. Well, I don't cut it there. I lift it into a space where I cut it, and the hyperplane works beautifully. And so in many ways, this is an easy one because you can actually see what you did. But when you have very high dimensional data, this is very difficult to see, except for things like this happen. And so what you do is you project into a lot of variables to see, can I cut it with a plane up there? And the reason this has been such a successful technique is because in practice, it has worked incredibly well. Before neural networks, support vector machines and the classification trees were the workhorses of industry. This was machine learning before deep neural nets, and it was industry practice to use these, okay? So this is a super powerful technique in this concept of lifting. And of course, if you lift, there is this issue about, okay, now it's going to cost me a lot in terms of computation time. So what am I going to do with that? Well, you start thinking about this, and one way to lift is through what are called kernel methods for support vector machines. I can either lift it up, or I can start thinking about, instead of projecting onto X, I'm projecting into some space. But what I'm actually going to do now is make linear functionals here where these are projections into higher dimensional spaces. So if I make these projections in higher dimensional spaces, I can pick these observables that actually encapsulate much higher dimensional feature spaces, okay? And one of these kernel tricks that we could use is to use something like a radial basis function. So in other words, I could project into functions like this exponent here, which is, notice what the exponent is. It's a difference between the data and your point. But if I expand that in a Taylor series, it gives me 1x, x squared, x cubed. It gives me all of these powers of Taylor series all wrapped up into one simple function. And so people really like this, or higher order kernels, because in some sense, both of them have Taylor series expansions, which are being captured here in my hinge loss as a sort of a very compact way to represent going to infinity, a computationally tractable way to do infinity. So kernel support vector machine, what it's all about is computation. How do I make computations faster? And so this kernel structure, if you pick good kernels and radial basis function is actually quite popular. It kind of gives you this very compact way to represent going to lots of directions, but in a compact representation that is computationally tractable. You still have the same loss function that we had before, but now you're projecting into a more complex space that's spanned by some kernel instead of like the linear discriminant. Okay, so you no longer just work with the linear discriminant plane, you work in a function of that linear discriminant plane, for instance, in this kernel basis. So that are the foundations of the ideas behind the kernel methods. And so it sets up a structure of optimization for you, allowing you then to start thinking about how to do this optimization. And again, support vector machines can be very expensive to run, right? Because now you're having to basically project all this data and draw a line, and very much like you would with linear discriminants, you've got to actually compute distances of all your data to the line. And so that's quite a costly computation. And then you've got to optimize this line across all of that data. So when you have very high dimensional data and you have a lot of data, both support vector machines or classification trees, all of them require quite a bit of compute time to actually pull out and do these optimizations, all of which were iteration schemes to walk towards the best solution that would be available to you. That's why kernel SVM becomes so important, because it allows you to do this computation in a much more efficient way and at scale. And so you need to start thinking a little bit about any of these methods are going to be costly. But of course, once you do it once and you have the trained model, now you have a classifier. You can bring new data in, make classification decisions based upon sound mathematical optimization techniques. And so that finishes our sort of overview, and we really covered linear discriminants, for which this support vector machines are sort of a generalization, but a very good generalization of. In fact, one of the most successful of the machine learning techniques before the advent of neural nets, and classification trees, which was the second of the most successful techniques and still widely used. So SVM, classification trees, still used quite a bit in practice, and we'll actually demonstrate those in code in some upcoming analysis so that you'll have some familiarity of how to use those techniques in practice.